Alright, in this video is just going to go through a couple examples and maybe make use of GeoGebra a little bit. Alright, so those shortcuts that we just discussed are wonderful. They save us a lot of time and energy, but there are some instances, cough cough project, where you might have to use the limit definition of a derivative. Okay, because it's not clear exactly what's going to occur. All right, so here we have a piecewise defined function. All right, and so you might have already guessed, but I want to look at the derivative at 0. Okay, so if I were to I could find the partial derivatives, right, of this function at any point not 0, right? So if I look at the partial derivative of f with respect to x and find the derivative with away from the origin, well, let's see, then I can use the quotient rule. So it's low d high, oh goodness, y minus high, and then d low, all right, with respect to x, it's just going to be 2x all over low, oops, y squared. All right. So that would be the partial derivative of f with respect to x at any point that is not the origin. Okay, but if I evaluate that at the origin, or say hint hint wink wink and try it, see what happens, it's just going to be a lot of zeros, right? So I'm going to get something that is 0 over 0 and not defined. Okay, and then if I want to look at 0 0, okay, what I need to do is, well, I need to do the limit definition. All right, so this is going to be the limit as h approaches 0 of, oops, of f of 0 plus h comma 0 minus f of 0 0 all over h. Okay, and I know this to be 0, right, by definition here. Okay, but then for this component, I actually have to use that first branch because I'm no longer in that case where I'm at the origin, I'm just pretty close. Okay, so then if I do that, what do I get? Alright, so here's the limit as h goes to 0. Okay, and let's see, if I put in h for x and 0 everywhere else, I get 0. Which is fun. So 0 minus 0 over h, so this is just 0. Okay, so I have that the limit here is going to exist, and so therefore the derivative is going to exist. Okay, but when I looked at the original function and just looked at the partial derivative of f with respect to x, it wasn't clear if it existed or not. So, the limit definition does have its place. Okay. Another example, oops, and I think I missed it. Let's go down here. Yep, here's the other one. All right, this one's a little more funky. Okay, and this time I'm gonna look at a different point. I'm gonna look at 1 0, and I want to determine if the derivatives exist. Okay, so I could try to differentiate this and have fun. Okay, well, I'm just gonna try the limit definition to start with and maybe save myself some time and energy. Maybe. Alright, so if I do f sub x of 1 0. Okay, so by definition this is going to be a limit as h approaches 0, and then I get numerator f of 1 plus h comma 0 minus f of 1 comma 0. Okay, I should also note that this point, right, 1 0, if I think about that in which branch of the piecewise function I'm going to be in, I'm going to be in that first one. Okay, and then I get that. All right, and after some computing, and you can verify this, I believe we get limit as h approaches 0 of 1 minus 1 over h, which is just 0. Oh boy, that's exciting. Okay. Alright, and if I look at the other partial derivative, this is f sub y. Let me write that a little clearer. Okay. Of 1, 0. Okay. I have the limit as h approaches 0, and then I have numerator and denominator f of 1 comma h minus f of 1 comma 0 all over h. Alright, and when I do this, alright, so this is limit as h approaches 0, numerator is 1 minus absolute value of h minus 1 all over h. Okay, and then the 1's are going to cancel, so I'm left with limit as h approaches 0 of absolute value of h over h. Now, if you say that this is going to cancel, I'm just going to cry. Okay, that doesn't, no. We're going to get plus and minus 1, and because of that discrepancy, we're going to say that this doesn't exist. Okay, and just to double check that, we can actually make this surface in GeoGebra. And that's another file that is located in the Google Drive folder. I believe it's called a double tent. And so here's the graph of that last function. Okay, and it looks kind of wonky. I kind of like it. All right, and we can rotate this around, I believe. And if you rotate it, you can kind of see all different angles of it. It's kind of fun. Okay, but long story short, here's our point that we were interested in, right? 1, 0, and then if you find the corresponding value of z, it would be 1. And here now, again, if we think about what we did previously geometrically, we were fixing a plane. So, okay, if I was looking at the x derivative, right, the y value would be fixed, and so I'd be looking right along that plane, and then when I create the corresponding tangent line, oops, that's not it. That's not it. This one. Okay, it would lie directly on top of one of those edges of that tent. Okay, so that one, yeah, that one's probably going to exist along that plane. Okay, but now if I look at the other plane, it becomes a little bit more interesting, and this is why it doesn't exist. Okay, so if I now am looking at the f of f sub y, that means x is fixed, and so I'm making sure that I'm on this plane somewhere, and on this plane, right, I can enable two other lines, and I can see that, and actually if we were to work out that limit, right, I said it could be plus or minus 1, and because of that we get two different tangent lines. Okay, so since the derivative is not well defined, meaning that there's precisely one value of it, that's why we're going to say that the limit doesn't exist. Okay, and since it isn't well defined, that's why we have two different tangent lines. Okay, but feel free to open this up and play around with it too. And that is going to conclude our examples in this video, and we have one more video that will finally define what it means for a multivariable function to be differentiable.